So, in this lecture, I will start a new topic, that is the foundation on collapsible soils. So, I will on foundation on difficult soils. So, I will discuss the foundation on two types of difficult soil. One is collapsible soil, another is the expansive soil. So, first I will discuss the collapsible soil, then I will discuss the how we can design the foundation on the expansive soil. So, now what is the collapsible soil? That the collapsible soils are the unsaturated soil, those undergo large volume change when they are saturated. Okay. Now, this volume change may be or may not be under the due to the application of additional load. So, that means suppose soil is unsaturated condition, and then when we saturate that soil, suddenly there is a huge volume change or a large volume change, even if we have not applied the additional load on the soil. So, that type of soil is the called is the collapsible soil. For example, suppose if we draw the E log P curve, I mean void ratio and the pressure curve. So, this is the log P axis and this is the void ratio axis. Now, from here to here, suppose this is the behavior under natural moisture condition. So, that means this is the path from say A to B is under natural moisture content. So, here soil is under say unsaturated condition. So, this is the behavior. So, that means there will be a decrease of the void ratio. Okay. So, there is a decrease of the void ratio as we increase the strength or stress. So, this is say E1. Okay. So, at that point we apply the stress Pw. So, this is we should say, so this is under natural water content. Okay. So, moisture content or under natural moisture content conditions. So, and then if we apply the stress, the void ratio will decrease, and then at this point B the soil is saturated. Okay. So, that means this is under initial from A to B is under an unsaturated condition or natural moisture content condition. Then when we apply the stress, then the void ratio decreases, and this is the AB is the path of that soil under natural moisture content condition. But at that point B, now the soil is saturated, but without applying additional stress, there will be a large volume change. Okay. So, there will be a large volume change. So, this will be the now path. So, that means we have not applied any additional stress, but there is a reduction of the void ratio. Okay. After that, if I apply the stress, then it will behave at saturated condition. Okay. So, then again it will behave at saturated condition. So, CD is the path for under saturated condition, but at the saturated point, so or the saturation point, you can say there is a large volume change without application of additional stress. But after that, when the collapse is done, then or volume change is large volume change is occur, then if I apply the stress, then soil will also go undergo a path C to D, which is under saturated condition. So, this type of soil behavior is called the collapsible soil, and we have to design foundation for this type of soil. So, now where the source of moisture, because we know the soil is a natural moisture content condition. Now, if suddenly the moisture content in the soil increases and soil becomes saturated, and then it will collapse. Now, what are the sources of this moisture? The sources of this moisture, the leak of the sewage pipe, drainage from the reservoir, broken water pipeline, slow increases groundwater level. So, because of these reasons the soil moisture content may increase, okay, and when the soil will become saturated, then suddenly there will be a huge volume change or the collapse of the soil. So, and then the foundation will also undergo huge settlement. So, this is the reasons, and this type of soil is called the collapsible soil. Now, the wind deposited sand or silt, basically the eoline soil, and these soil deposit higher amount of void ratio, less unit weight, it can be cohesionless or have site cohesion. So, this type of soil, there is a probability that they may be collapsible soil. If the cohesion is there in little amount, then due to the saturation this soil loses its cohesiveness, or this cohesiveness, it loses its cohesiveness. So, the strength is reduced, or there is a possible amount of collapse. And if this is the wind deposited sand, then the void ratio is very high. So, because of this saturation there may be a large amount of volume change. Sometimes the soil may be residual soil that are product of weathering of parent rock. Now, that there is a term called collapse potential. So, by which we can identify that if the soil has some problem related to this collapse. So, this collapse potential is what? That we apply step loads on the unsaturated specimen at natural moisture content in a consolidation ring up to a pressure of 200 kPa. So, that means we place the soil sample in a consolidation apparatus, okay, or oedometer, and in the consolidation ring under the natural moisture content condition or under unsaturated condition, we applied the stress or the load on the specimen gradually up to a pressure of 200 kPa, and at that pressure the soil sample is flooded for saturation. That means, soil sample is now saturated and we left it for 24 hours. And then we measure the change in void ratio. Okay. So, that means, here it will follow the same path. That means, from A to B, PW will be in that case the stress that is applied at point B will be 200 kPa, and then at A to B it will follow the path for the unsaturated condition or natural moisture content condition. Then it is flooded and kept it for 24 hours, then it will go from A to C. So, we will measure E1 and we will measure E2, okay? And then we will write this collapse potential. So, that is E1 minus E2, 1 plus E0. E0 is the natural void ratio of the soil. Now, if this collapse potential is 0 to 1, then it is okay, no problem. Then 1 to 5 there is a moderate risk or trouble, then 5 to 10 it is trouble, 10 to 20 it is severe trouble, and greater than 20 it is very severe trouble. So, depending upon this collapse potential. So, when you do the consolidation test, if we find that this collapse potential is very high or it is within the risk zone, then we have to take care for this type of soil when you construct the foundation over it. Now, how I will calculate the settlement on foundation of settlement of foundation which are constructed on the collapsible soil. So, for this purpose 2 samples are required. So, 2 samples are taken. So, and then both the samples are placed within the consolidation ring or the consolidation apparatus, that is the oedometer apparatus, and they are placed under a 1 kPa stress, okay, and they are kept for 24 hours. So, that means we have taken 2 samples and both the samples are placed in oedometer apparatus or the consolidation apparatus, and a stress of 1 kPa is applied on both the samples, and both the samples are kept for 24 hours. Okay. So, and now at this situation both the samples are under natural moisture content condition. Okay. Now, after 24 hours one sample is flooded for saturation and another sample is kept still under natural moisture content condition. Okay. So, now we increase the load gradually on both the sample, one is under natural moisture content condition and another is under saturated condition, and then we will get the path for, and we will measure the volume change for every load increment, and then we will get a path for saturated soil and unsaturated soil or soil under natural moisture content condition. So, I will show you how we can calculate this collapse settlement. So, I will show the two cases, one is normally consolidated soil, one is the over consolidated soil. Okay. So, suppose this is the E value. So, now E curve. So, this is the path, say sample under natural moisture content. So, this is the path for sample at natural content. Now, we have applied a P0 stress here. So, that P0 is basically what, and there is a P0 plus del P also. Now, what is P0? P0 is the in situ, I should write here because I will draw the two curves side by side. So, P0 is in situ effective overburden pressure and del P is the increment of stress due to construction of foundation. So, that means I mean it is the stress is applied up to P0. So, at the P0 that means the soil will undergo the effective overburden pressure that it is subjected to in the field, and then we will add additional amount of stress del P, that is the increment of stress due to the application of the or the construction of the foundation. So, this is the line of P0 line and this is the P0 plus del P line, and this is the path for natural moisture content condition. So, now this is, then I will get another path This is the path of this soil. This is the path of this soil under saturated conditions. So, this is we have taken two sample, one is under natural moisture content condition, another is saturated condition. So, this is the path for saturated conditions. Now, I should write this curve properly. So, it will come so this is the curve. Okay. So, what I will do from this curve with the saturated condition, I will determine what is the pre-consolidation pressure. So, that procedure is been explained in your soil mechanics course. You can use the Casagrande method, okay, by which from this curve you can determine what is the pre-consolidation pressure. So, for example, that pre-consolidation pressure is this one, say. Okay. So, this is your PC. So, this line corresponding to is PC, which is pre-consolidation pressure. So, what is PC? PC is the pre-consolidation pressure. Okay. So, now if that PC divided by P0 is equal to 0.8 to 1.5, then that soil is called normally consolidated soil. Okay. And or you can say in short NC, and if PC divided by P0 is greater than 1.5, then it is over consolidated soil. Or OC. Okay, so this curve that I am drawing, this is for NC, normally consolidated curve, soil. So, once I get the PC value, then I will extend this line, okay, this straight portion I will extend. This straight portion is extended, and that it will say this point. So, this point corresponding to this E will give us E0, and this coordinate of this point will be P0 and E0. Okay. So, this is the point E0 and P0. Now, I will draw a curve which is same as this natural moisture content curve. So, I will draw the same curve. Actually, this curve is slightly, this will be the curve actually. Okay. Oh, anyhow, so let me draw it again. Fine. So, this is the curve which is same as the natural moisture content curve. So, that I will draw from this point. So, this curve is same as this curve. Okay. So, that means this curve is same, both are same. Okay. So, we have drawn this natural moisture content curve. Now, where it is cutting with this P plus del P point. So, there I am drawing one line, and here also I am drawing one line. So, this point, this value is E del E2, and this value from this point to this point is del E1, and definitely this is not in proper scale, but this is the value. So, that means what does it mean, that from this original point to this P plus del P point for the natural moisture content curve, the settlement or the void ratio change is del E1, and for the saturated sample the additional void ratio change is del E2, and that is the change in void ratio due to the collapse of the soil. Okay. So, and similarly I can draw the curve, similar curve for over consolidated soil. So, for the over consolidated soil also I can draw the similar curve log P. So, this is again P 0, then this is del P plus P 0 or P 0 plus del P. So, for the over consolidated soil, so again the this curve, this is for the normal moisture content curve. This is for normal moisture content at natural moisture content. Okay. So, this is for over consolidated soil. So, we have this P 0 line and we have P 0 plus del P line, and then we have the soil which is under saturated condition. Okay, this is the soil under saturated condition. Okay. So, this is at saturated condition. So, what we will do? We will, because here we will locate this point, because it is already a straight line. So, extension is not required, because here the straight line portion is been extended. So, this point will be treated as P 0 E 0 and this value will be E 0. Then we can so this is my okay. So, there is a point. So, I have to draw this curve, because this is say PC line. So, up to that this is one change in line, then there will be one change in slope. So, that means here then there is a change, then there is a change. Okay. So, that means this is a straight line almost. So, we have already located. So, that means here we locate the PC point, and then this is the E 0, and then we can take this point and we can draw now the same curve which is from here, which is for natural moisture content. Okay. So, again this curve and this curve is same, and then we will take this point also. So, this will give us del E 2 and this will give us del E 1. Okay, the same way, but two different soil. Now, how I will get the settlement? So, settlement of soil without change in natural moisture content that is S I is equal to del E 1 divided by 1 plus E 0 and H. Now, H is the thickness of the soil layer. Okay. This is the thickness of the soil layer or collapsible soil layer. So, we will get E 1 value from here. So, that settlement is without change in natural moisture content. So, that will be del E 1 and plus 1 1 plus E 0 into H. Now, the settlement of soil caused by collapse in the soil at saturation, because of this saturation there will be a collapse and that settlement is S2. So, that will be del E2 1 plus E 0 into H. Again H is the thickness of the collapsed soil layer. Okay. So, this way we can calculate that what would be the settlement of the foundation. The next one is that how I can calculate the bearing capacity of the foundation in collapsible soil. So, we have to do the field test or field plate load test. So, once we get the plate load test data, so we will find, so this is the load versus settlement. Okay. So, we will find that this type of curve will be there. So, this is the loads versus settlements and there will be a sudden fall of the curve, okay, like this, or there will be a very quick duration, there will be a huge amount of settlement, or there will be a sudden fall of the load or settlement, there will be huge settlement. So, this point is called pre-critical. So, these are called critical stress or critical pressure, or we can say this is the sudden breakdown at these points. Okay. So, there will be sudden breakdown at pre-critical. Now, the P allowable will be pre-critical, we have to determine, divided by the factor of safety. So, generally this value is taken as 2.523, and this type of behavior is very common for saturated condition as compared to the dry soil condition. So, this way we can determine the settlement of the foundation on the collapsible soil, and we can, if I do the plate load test, we will get the bearing capacity of the foundation on collapsible soil. Now, still we can take some precaution when you construct foundation on the collapsible soil. So, the continuous foundation are safer than the isolated foundation on collapsible soil that can effectively minimize the differential settlement. Okay. So, this type of load bearing beams we can provide to connect the columns. So, that there will be a continuous type of or a type of foundation, is not a isolated footing. So, isolated footing is not a good idea. Okay. So, we can provide this type of foundation, and then if the upper layer is 1.25 to 2 meter, this upper collapsible soil layer is 1.25 to 2 meter, that soil is get wet and collapse at the same time. So, it is recommended to use the heavy roller to compact the soil layer. Suppose if the collapsible soil layer is a shallow depth or shallow thickness is small, then we can apply the heavy roller to compact this soil. So, suppose as I mentioned, so this soil has a very high void ratio. Now, if we compact this soil and then we can reduce the void ratio, then we can minimize this collapse of the soil or minimize this settlement. So, and rather than spread footings and wrap may be constructed over that compacted soil. Now, foundation can be compacted over the compaction soil, or alternatively we can use the dynamic compaction also. So, can be used to compact this soil layer. So, these ground improvement techniques, dynamic compaction, vibro flotation. So, these are all the common ground improvement techniques. So, those are taught in your ground improvement course. So, you can see, so any ground improvement book or any ground improvement course, then we will find what are these techniques. But here there is no scope to explain all these ground improvement techniques in this course. So, that is why I am just giving the name. So, what are the techniques you can use to minimize this collapse of the soil. So, that means one is you can provide the heavy roller, or you can provide the dynamic compaction to minimize the voids and to minimize the collapse, and then we can construct the foundation over this compacted soil. Now, if the soil layer depth, that means collapsible soil layer depth is large, so that is 10 meter, then we can provide the vibro flotation, which is suitable for free drainage soil, and that means we can provide vibro flotation to compact the soil. Or there is another option, that if I saturate the soil, or that is called the ponding, if I saturate the soil before the construction. So, in my in the first picture I have shown, so this is my settlement. Okay. So, this is the unsaturated condition, then soil has been saturated. So, then there will be a collapse or large deformation. Then if I apply the load, then it will follow condition on the saturated stage. Okay. So, that means if before the construction, if I do that collapse of the soil by saturation, and then we will follow this C2D part when the load is construction will start, when the load will apply. So, that means that sudden collapse or sudden void ratio increase or volume change increase will not happen. So, that means either we can compact the soil, or we can make the soil saturated, so that there will be, you will get the collapsible volume change before the construction is started. Okay. So, that is these are the options. Now, if the pre-collapsing of the soil is not possible, then or the compaction is also not possible, or the pre-collapsing is not possible, then we can extend our foundation beyond this wetting zone or collapsible soil zone. So, by providing piles. So, these are the techniques by which we can minimize the risks of the collapsible soil settlement, or the huge volume change or large volume change on the foundation, and then we can calculate the settlement of the foundation on collapsible soil, and then this value the settlement is acceptable value is say up to 30 centimeter. So, that means this collapsible soil settlement. So, this is up to 30 centimeter is okay. So, that means this value should not be greater than 300 millimeter. So, that means we have to make our foundation such that, so this up to 0.3 meter or 30 centimeter or 300 millimeter settlement, it is okay, but it should not be more than that. So, we have to calculate that also. We can calculate the load carrying capacity of the foundation by using plate load test, and then once the foundation will be constructed, if the soil is collapsible soil, then we can improve that soil by using vibro flotation if the thickness of the soil zone is large, or for shallow thickness or the shallow depth, we can provide dynamic compaction or the heavy roller, or we can go for the ponding also. If these are not possible, then we can extend our foundation beyond the wetting zone by providing pile foundation. So, in the next class, I will discuss the foundation on another type of difficult soil, that is the expansive soil. Thank you.